All right, let's see what day 2 is all about. Advent of Code 2019, day 2. 12:02 program alarm. On the way to your gravity assist around the moon, your ship computer beeps angrily about a 12:02 program alarm. I'm seeing the link goes to a NASA website. Let's take a look. Oh, there must have been a 12:02 program alarm in when they landed on the moon then. I'm not familiar with that, but I do remember there were some issues landing. On the radio, and Alf is already explaining how to handle the situation. Don't worry, that's perfectly normal. The ship computer bursts into flames. You notify the elves that the computer's magic smoke seems to have escaped. The computer ran int code program. Oh, right. 2019 was the year of int code. Int code programs like the Gravity Assist program it was working on. Surely there are enough spare parts up there to build a new int code computer. Right, so we need to create a separate crate for this, because I remember the int code gets used in multiple problems for 2019. And I don't know if I should start off by just making it here and then switching over to a separate crate, or if I should just start off right off the bat in a separate crate. Can I actually put it at the same level? Right, I should just be able to create an int code module. Let's do that. Let's do that. We'll just create, instead of a separate crate, we'll just make a module for it and then just include that everywhere. So if I say edit source int code.rs, I should be able to say pub struct int code and import that. Right, and then use int code star. Will that work? Oh, maybe I have to say create encode? No. Super encode? This encode? AOC 2019 encode? You should be able to import modules, right? Oh, I have to say mod encode. File not found now. Okay. Oh, I have it under this. Super. Nope, you can't do that. Oh, maybe I have to put it in main then. Nope, this is the wrong main. I need the main for 2019. Yeah. So can I say mod int code here? And then I can say create int code. And it's saying remove the whole use item because we're not using it. Yeah, that's fair. All right. And we're never constructing this. That's fine. So we're going to figure it all out as we go along. All right. So an int code program is a list of integers separated by commas, like 1, 0, blah, blah, blah. To run one, start by looking at the first integer called position 0. Here you will find an opcode, 1, 2, or 99. Opcode indicates what to do. For example, 99 means that the program is finished and should immediately halt. Encountering an unknown opcode means something went wrong. Opcode 1 adds together numbers read from the two positions and stores the result in the third position. The three integers immediately after the opcode tell you these three positions. First two indicate the positions from which you should read the input values, and the third indicates the position at which the output should be stored. For example, if your encode computer encounters 1, 10, 20, 30, it should read the values at positions 10 and 20, add the values, and overwrite the value of position 30 with their sum. Opcode 2 works exactly like opcode 1, except it multiplies the two inputs instead of adding them. Again, the three integers after the opcode indicate where the inputs and outputs are and not their values. Once you're done processing an opcode, move to the next one by stepping forward 4 positions. Okay. So we're gonna read the position 9 and 10 and store it in 3. Okay. one addition, right? The two opcodes are 9 and 10. Handle this opcode. First, you need to get the value at input positions. Position 9 contains 30, and 10 contains 40. Add these two numbers to get 70, and then store it. So we're overwriting the values here. All right, so if we use this as an example program, it means that the final program should look like this. And then we have a few more here to mess around with. Okay, so there's only two opcodes. That makes it pretty easy. I guess what we can do is store the data as a vector in here. We'll just call it memory. And I don't know if we're going to have to be dealing with how big the range of numbers is with these things. Obviously, we can get up to 3,500. Maybe we just make it I64 and live with that. Import int code. So I want to be able to create a new from a string of numbers, right? So I can just copy and paste these things here. Bubfun new from string. And we'll just say stir. And we're just going to return a self. And this is just going to be a comma separated list of numbers. That's it. So that's all we care about. So we're going to say int code memory is going to be s.split, comma, map num parse I64, like that. Probably num is good enough. And then unwrap. We're just going to blow up if it fails. And then collect. Yeah, it doesn't like that. Parse not found in the scope. Oh, no, we do have to say num parse. I was right the first time. This is how stale I am at this step. Okay, so now up here, we're going to put an int code computer. Yeah, but we don't have a default. We should just have an empty. So code computer int code. Like that. I know it's never read. Okay, so now in parse here, actually what we're going to do is we'll flip over to the test side of things here. And we're going to say for test, let's make a mod test. Use superstar. Oh no, we're going to make these tests in here. All right, we want to make sure these tests work. So this is test fn example 1. Actually, let's just see if we can do an add. Right? Let's just do one operation at a time because we have operation 1, which is add, and operation 2, which is multiply, and then operation 99, which is halt. That's additional state that we'll need. Something's wrong. Why is it not? Oh, that's why. So test add, right? So we just say let int code or computer is equal to int code new from string. And we'll say we're going to add 1. 1 is the add instruction. We're then going to say we're going to add from positions 0 and 2, right? Because 0 will be this guy, and then 2 will be itself. And we're going to store it at position 0. And if I run it, make up a function called run, then the result should be a vec of, we're adding 1 and 2 and putting it in position 0, so it should be 3, 0, 2, 0. Computer memory. And we don't have run yet. So let's make a run. Pub fun run. If we run off the end, does it? Oh, 99 just means stop. Okay, so maybe we'll stick a 99 on there. In the other programs or other VMs that he's invented, say if you run off the end, you halt. It says encountering unknown opcode means something went wrong. So this has 99 in it. These all have 99s. That's interesting. Yeah, so we just have extra code at the end there. That's fine. All right, so we're expecting the 99 to halt. Maybe we should test halt. Let's do this. Just make sure we can halt. Fn test halt. And we'll just grab a new computer here, which just has 99 in it. We say run. And then we should just assert that the computer is not running. Computer running. Yeah, and now we're writing the run thing. So we do need to take a mutable reference to self because we're going to be changing memory as we go along. So run, this is while self running self step. That was easy. Okay, so now pub, oh, this should be fun. Step also takes a mutable reference to self. And now we're going to look at our current opcode. So we need a program counter. Instruction pointer. Yeah, let's call it instruction pointer. And that's going to be usize because it's going to be a vec into, or an index into the vec. I don't know why it keeps putting that in the wrong spot. Okay, my indentation thing is wrong. Okay, so now we're just going to match on self memory of self IP. Might not be able to do that because I'm about to modify memory, aren't I? So if it's 99, then we're going to halt. Self running is false. Everything else is an unimplemented instruction. I'm going to preemptively copy this. Okay. Oop, like that. Okay, so if I run tests, test halt did not run. Why not? Why didn't these tests run? Are we not including this? Yeah, I know these guys aren't read in regular mode, but in test mode, we should be running the tests. I have a test right here. Okay, there it is. Oh, okay. So this is working. It's just that we're getting this error. Okay, that's a little frustrating. Megan says it does say pass. Yeah, it did say pass, but I was looking for that line, and Bacon test kind of. It says, okay, well, your test passed, but we're getting some warnings here, which we will deal with in a second. Actually, yeah, let's just do it now. Oh, I don't have it in my Git files yet. How about now? 1902. There we go. So let's just, oops, let's just comment this out just for now. Just so I can see my test. Okay, I'm happy now. All right, so now we're able to halt. Let's try testing the add function. So this should fail right now because we don't have an opcode, right? So it panics. So let's add the add function. We're going to read memory from 1, 2, and 2. A equals self memory of self IP plus 1. And B is going to be self IP plus 2. And let dest is equal to self IP plus 3. And then we're going to say self memory dest is equal to self all right. These are the locations. This is the location that we're trying to read. Yeah. So we don't want to do this. We're saying this is the dest. A plus B. All right. So let's see if that test passes. We're stuck in an infinite loop. Oh, I know why we're stuck in an infinite loop. Because I'm very silly and I didn't increment the instruction pointer after each execution. Self IP plus equals 4. All right. And it failed. Oh. Oh, this was right. Self memory, self IP plus 3. We're getting the address of what? That's an I64. That's an I64. Oh, as usize. Still failed. Did I do it wrong here? I'm saying I'm expecting 3020 and it's getting a 2020. Oh, we do need to reread. Because these are addresses. I should probably do the similar thing of making these indexes like I did with the slowpoke thing. All right. All right, now we have everything testing. So we can add, and then multiplication should just be very simple now that we've stumbled our way through addition. One times 2 is 2. Actually, what I could do is I could just say 2 times 99, right? So it's position 0, 1, 2, 3, and 4. So if I say multiply position 4 by 2 and store it in position 0, we should have 2 times 99 there. And this should panic. It does. So now we can do this and change the plus 2 in multiplication. Oh, right. I got to change that value as well. There we are. Okay, so now multiplication works. So now we should be able to actually run the a full program, right? So test fn test example 1. And it's just going to be this whole thing, and it should end with this whole thing. Do we want to check everything? I guess we do. Like that. Look at that. Example 1 worked. Yay. I guess we could test the remaining ones. Or we can say, we can put them all in here, right? And this is where it'd be nice to have a little test runner that would do all the work for us. Test day 2, part 1. Let's do it that way. And then what we can do is change this to a vec of tuples. Let matrix equals vec bang this, comma, oops. This. Right, so we have the string first and then the answer next. And then this closes that. And then we can just do the same thing for the remaining ones, right? This becomes this, comma. This becomes this. This longer one, slightly longer one, becomes this. And this final one here turns into this. And now we'll see what Rust format does. Oh, that's not too bad. Okay, so now we can just loop over the matrix for entry in matrix. New from string entry.0, run the computer, and assert that it's equal to entry.1. What's not happy? Oh, I got to close the 4. There we go. All right, so part 1 works. Oh, I think that gives me confidence in our program now. Viewer 2 says, why AOC now? This is a warm-up. This is a warm-up for AOC. It's coming up in less than a month, and I want to get good at it so that I can blast through all the programs, or all the puzzles that we're hit with. And we'll see how that goes. Did we get a puzzle input? Not yet. So copy input day02.text. Throw that in there. Oh, I don't even know what we're looking for. So if I want to run it, oh, there it is. What value is left at position 0 after program halts? Oh, wait. Before running the program, replace position 1 with the value 12 and replace position 2 with the value 2. And then what's left at the position 0 after the program halts. Okay. So this is our input. So we should be able to just read the input. Oh, yeah, as a string. That works, right? So we can use this. I already have a from string. So we say self computer equals int code new from string. Was it read to string? Uh-oh. That was AOC lib. Read lines, read single line, read numbers, read to chars. I guess read single line is what we would want. Input day02.text. Let's see if that works. Do we get a computer out of this? Arguments to this function are incorrect. What do we need to pass in? Is the path name? Oh, vec_char. Ah. So I could just do a read to string with an expect. That might be the simplest thing to do, right? We have standard fs read to string. Let's just do that. Int data equals input deo2.text, expect file not found. And then we just replace this with int data. Expected stir found string. Tests are working. If I run it, we panic. And a parse int error invalid digit. Oh, because, yeah, because there's the new line at the end. I'm going to make this really wacky. Split once on a new line. Didn't like that. Oh, and then expect missing new line. How's that? Okay. We still have an error here. Creates a temporary value. Really? Okay, so we have to actually create the input to avoid the temporary value, and then we can split once on that. And that way we have it in memory. All right, so I should be able to do a run now, right? And then get, first I have to insert, replace position 1 with the value 12 and position 2 with the value 2. Oh, okay. So that means I need to have a poke instruction, I guess. Self computer poke at position 1, 12, and poke position 2 with 2. And then self computer run. And then after it's done running, we're going to output what's left at position 0, self computer peek 0. So I have to write a peek and a poke. Of course, they don't exist. So we're going to generate a poke method and generate a peek method. And we're going to implement them. Let's write a quick test here. Fn test peek. So we can just grab this and then loop over each one. Assert EQ to computer peek position 0 or to 099. That's peek 1, 2, 3, and 4. All right, these should fail. We're putting I64s in there. And test peek failed. Okay, so all this is self memory of arg as usize. The test passes. We're not seeing it pass, but that's okay. And then I should be able to poke. So test and test poke. What we'll do is actually grab all of these. We'll set this up, and then we'll say computer poke at position 1, 2, 3. The value 1, 2, 3, 4. And then change this to 1, 2, 3, 4. Everything else should be the same. Test poke failed. So let's fix poke. Oh, this should be I64. This should be I64, and this should be a usize. Self memory arg1 address is equal to value. So we're going to rename this to address as well. And value. And just hang out for the train to go by. Oh yeah, we are poking it. We're not returning. I don't know why it thought we were returning anything. Okay. This does need to be mutable. All right. So now that's that. Oh, line 85 in the test does not need to be mutable. Okay. All right. Now all of our tests pass and we can actually see it. So if we flip back here, let's try running. And we get a number, 47147001. Let's try it. See what happens. Could be good. Could be bad. And it is the right answer. Yay! Okay, so git status. How do I want to work this? Git restore staged. This guy and this guy. I want to put int code in separately. Git add source int code, git status, right? So we're good. Git commit -m, the start of the int code virtual machine. Add source. And now we have our code, right? Git commit -m 2019 day 2 part 1. What did I change in git log? Oh, I added this. This should have been part of the first push. Git add cargo lock. Git commit -m. Oops. Need to add AOC lib as dependency. There we go. And then I should remove these test input files. AOC 2023. Okay. We clean? We clean. All right, let's continue to part 2. Good, the new computer seems to be working correctly. Keep it nearby during the mission. You'll probably use it again. Real Encode computers support many more features than your new one, but will let you know what they are as you need them. Right. Yeah, so as we went along, we added more and more. I remember that part. Even if I don't remember the puzzles exactly. However, your current priority should be to complete your gravity assist around the moon. For this mission to succeed, we should settle on some terminology for the parts you've already built. Encode programs are given a list of integers. These values are used as the initial state for the computer's memory. When you run an encode program, make sure you just start by initializing memory to the program's values. Position in memory is called an address, right? Opcodes like 1, 2, or 99 mark the beginning of an instruction. The values used immediately after an opcode, if any, are called the instruction's parameters. For example, the instruction 1, 2, 3, 4 is the opcode, 2, 3, and 4 are the parameters. All right. We're getting our terminology down. Instruction 99 contains only an opcode and has no parameters. The address of the current instruction is called the instruction pointer. It starts at 0. After the instruction finishes, the instruction pointer increases by the number of values in the instruction. So I was always adding 4. So you add more instructions to the computer, this is always 4, right? So we're going to need to, in this, the step function is going to need to be able to tell us how far to step by. The halt instruction would increase the instruction pointer by 1, but it halts the program instead. The terminology out of the way, we're ready to proceed. To complete the gravity assist, you need to determine what pair of inputs produces the output of this. The input should still be provided to the program by replacing the values at address 1 and 2, just like before. In this program, the value placed in address 1 is called a noun. The value placed in address 2 is called a verb. Each of the two input values will be between 0 and 99 inclusive. Oh, okay. So we can just brute force this. Once the program is halted, its output is available at address 0. Also just like before. Each time you try a pair of inputs, make sure you first reset the computer's memory to the values in the program. In other words, don't reuse memory from a previous attempt. Find the input noun and verb that cause a program to produce the output. This. What's the 100 times the noun and the verb? Oh, 100 times the noun plus the verb. Right. And that makes sense because the numbers are between 0 and 99. All right, so let's expand our int code to be able to reset. Which means reset. we're going to make this let instruction list is equal to this guy. Right? And then memory is going to be instruction list.clone. Actually, we just call this reset. And then we had reset here. Oh, it didn't work. Vec I64. I would have thought that this would have told it the information it needed, but I guess not. All right, so now we're going to add a reset function, which we need to test. Test fn can reset program. So we're going to run a complicated one. So we can say let mut computer equals int code new from string. I guess I called this new from string because I thought I would be doing new from file as well, but there's no reason to. There's no reason to. Let's just call it new. And then what we'll do is we'll run the computer run. We know from this test that the output is going to look like this. So now I'm going to make a function called computer reset. And now I want this to look like this. Assert EQ. The original memory, computer memory. We need that. We don't have, oops, what did I just do? It looks like it deleted a bunch of code there. So let's generate a reset method. It does need to be mutable and it does not return anything. So we're going to just say self memory equals self reset clone. And let's test. Test reset works. So now we can go back to 1902 here. And part 2 is just going to loop over all the nouns and the verbs. For noun in 0 ... equals 99. For verb in 0 ... equals 99. Self, oh, we can just say, yeah, self computer poke. The noun goes in 1 and the verb goes in 2, right? Address 1 is called the noun. Yeah, okay. So poke 1 for the noun. Computer poke 2 for the verb. Nount. And then we'll say self computer run. And then we say if self computer peak at 0 is equal to this value. Yeah. Then we're done. We say return AOC lib output, and we're going to return 100 times the noun plus the verb. I did count again. Otherwise, we're going to continue, and then we're going to say panic value not found. Oh, we have to do a reset. Computer reset. Oh, it's a private method. Oh, interesting. It put pubcrate on here. Doesn't need to be pubcrate, but that's fine. All right, so we run. Value not found. Okay, so we have a bug. What's the bug? Oh, I need to reset it because I ran it in part 1. Duh. So let's just reset it before we run. Value still not found. All right. What's wrong? We can say println for noun, verb, self, computer, peak, 0. And we could just print them all out. And I'm going to do it this way so that I don't have to flood my bacon. Cargo run, less. It's always 1. Oh, I forget. No, I'm running it right here. But we know that if we run it this way, it worked, right? We got the actual value. Oh, these are all for... Oh, that was the panic message, yeah. We know that 12,02, 12.2. Okay, so I must be doing something crazy here. We do the run. Oh, I am an idiot. Self-running is true. Actually, what I should do is say false, because it's not running yet. Right? Running should be false. Actually, what I can just do is say self default. Right? And then when somebody says run, self-running is true. Because we're running it now. The reset, we don't need to do that. Okay, so I think that was the bug. That was kind of a dumb bug on my part. Let's get rid of this print statement because otherwise we're going to get flooded. Bacon run? No. If we say, all right, let's put the print statement back in. Oh, it's panicking. It's panicking. I'm sorry. I misread that. So let's go back to int code line 49. Instruction not implemented. 0 not implemented. At IP. Oh. $124. Yeah, we can reset the whole thing. I mean, the 10 reset program test works. This was supposed to be super easy. It's day 2. If I'm struggling on day 2, this is a problem. Right? Oh, right. I got it. Self IP equals 0. Okay. That's something else. Okay, let's add that to the reset. Cert EQ 0 computer IP. All right, that should fail. All right, thank goodness. And then we'll just put it back. Okay, now if I hit run, we get 1 million of output. So let's fix that. 5121. All right, let's see what happens. Let's copy paste so I don't make a mistake here. That's the right answer. Yay. Okay. Git status. So git add source int code, git commit -m upgraded int code computer VM to handle resets. And then git add source, git right? Yeah, git commit -m 2019 day 2 part 2. All right, I do have a little more time.